There was one more question about this one here, and I think it's a good question. Listen. We say the lift and drag must act on the neutral point if the CG is over here, so that CM alpha is equal to 0. But how can I still say that lift and drag is acting on the neutral point if the CG moves to the front? The reason is that the lift and drag is only a function of the geometry. It's not a function of the CG. Lift and drag is a function of the geometry. So if I move the CG from here to here, lift and drag must still be acting on the neutral point, because the point of action of lift, drag, and aerodynamic moment does not depend on the center of gravity. Is that okay? All right. So next thing I want to look at is the effect of alpha, the angle of attack, on the whole aircraft. Okay. Let's put this one over here. Okay. So the way we're going to approach this is that CL of wing body is equal to no, this is wrong. Just give me a second. Let's do this one. Okay. This is equal to wing body times alpha wing body. And that is CL alpha wing body. Okay, this is the lift curve slope. Let's put an A in terms of lift curve slope. Okay, this is what we call the lift curve slope. Someone asked me the other day, well, CL alpha graphs for a symmetric airfoil looks like this, and it's 0 alpha, this is CL. But how about this one, right? For many airplanes or airfoils, the CL alpha graph looks actually like that, right? So then CL, for this thing, CL is equal to CL alpha times alpha. But here, this is CL0 plus CL alpha times alpha, right? That was the question of some people. I'm just saying, so whenever I write something like that, you know, CL alpha times alpha, the question is always, oh, is this only true for a symmetric airfoil or a symmetric airplane? That's not really the case. You see, this is just a reference, this is just a coordinate system. It would be possible to just move this coordinate system over here. Okay, so it would be, and then suddenly you have a graph that goes through 0, and the only difference would be the reference point would have changed, and you can still write these equations instead of writing always adding a constant plus CL0. You could just move the reference point. When you write something like this, when I write something like this, I'm just thinking that the reference point has moved from here to here, so that this actually goes from 0 to 0. But I know that a 0 here, a 0 alpha here, really doesn't mean 0. It really means -2 or something. Okay? You don't believe me? So this is basically not alpha anymore. This graph here is now alpha -2, and I call this alpha head. And everywhere I can write alpha head. And at the end, when I calculate something, I just say alpha head is equal to 0. But in reality, I know alpha is equal to -2. It's just a conversion of references. Does it make sense? No? If you don't understand this, go home and think about it. I mean, it's really simple mathematics, okay? So, okay, this is this. For the tail, it is equal to AT times alpha t. AT again is CL alpha of the tail, and it is the lift curve slope for the tail. Okay. Now here's an interesting thing though. The alpha tail, okay, the alpha tail. You know, you have the airplane, and you have the wing, and then the airplane has an alpha, okay, and this alpha we call the alpha wing body, the alpha for the wing body, okay? And sometimes the wing has its own attachment, the angle of attack, so you need to add that to this number, whatever. But at the same time, at the back, we have our horizontal tail. Now the horizontal tail can also be a controlling surface, right? That's how the pilot controls. We call it the elevator. Sometimes the whole horizontal tail can move. Okay? The whole horizontal tail can move up and down. So effectively, the pilot can change the angle of the horizontal tail as a whole and change the angle of attack of the wing, of the horizontal tail. And therefore produce extra moment to move the nose up and down. Then we would call this a horizontal tail, but I would also call it an elevator. Okay? However, sometimes, if this is the horizontal tail, right, sometimes you have this part will move only, and this is what we call the horizontal, the elevator, right? The pilot can move the back of this thing up and down, and this is what we call the elevator control, right? We call it del E, elevator control. And what he's doing here is, if it's a big tail, right? If it's a big tail, it's actually increasing or changing the shape of this airfoil, let's say, and make it a little bit more cambered to produce more lift. But if it's a small horizontal tail, this might not be enough to move that little piece there. Instead of that, what you can do is you can have a horizontal tail like that, and you might have an attachment point and actually move it like that, right? You can move it up and down. So you can change the direction of the whole horizontal tail, right? You can move at the back. This is all horizontal tail. Horizontal tail. Okay, so you can move it up and down. This would be still an elevator. Let's look at this one here, okay? Because this is an easier one to look at and easier to write. So let's look at this one. So I'm just saying that if you do this, okay, this angle we could call IT. Okay, so what I'm saying is the alpha tail for this one would be the alpha wing body, okay, minus IT, the kind of the pilot control. And you see that a positive IT in this case will induce a negative alpha. Okay, so moving it downward would be a positive. Would be a positive IT. So I call it a pilot control. So the pilot can adjust the angle of the horizontal tail. So therefore, it will change the angle of the tail. Okay, this is one thing. The second thing is, which is kind of important, is if your airplane is not too long and you have a horizontal tail over here, and let's say the wing is too close to the horizontal tail, I'm going to exaggerate this a little bit. What's going to happen is that when the air moves towards the wing, it will bend slightly downward, right? We call it the downwash. And if you push down enough air, you will pull yourself up, right? This is kind of, this is one explanation of how airplanes fly. You are taking the air and you are bending it so that it moves a little bit downwards. And when it moves downwards, if you look at the total conservation of momentum, the airplane will keep itself up, right? So without the downwash, you can't really fly, right? I mean, if the air was just going straight like this, you wouldn't be able to pull yourself up. So because of this downwash, you're flying, okay, but if the downwash is coming onto the horizontal tail, then you are really changing the angle of attack, because suddenly you have a horizontal tail, looks like that, and the downwash has an additional component, has a component that's coming from the top onto that horizontal tail, so it's kind of blowing from the top, right? So this is what we call a downwash. And therefore you really need, and this is reducing the angle of attack, you see. If the angle of attack, if this was V infinity, and if V infinity was coming like that, this plus that will reduce the angle of attack, doesn't it? If you blow air from the top, which onto something that moves forward, it will reduce the angle of attack. Okay? And therefore I will add a downwash component here, minus eta here. Okay? And this is like the downwash component. Now you might claim that if the distance here is too large, then the downwash might in fact be equal to 0, because there's no effect from the wing to the horizontal tail. But often, even if there's a small effect, there is an effect. So we are just trying to put that. I showed you some pictures a few weeks ago where the horizontal tail is kind of at the top of the wing so that it's not affecting the downwash. Then the downwash is 0. But for the sake of keeping it general, let's keep that downwash over there. Okay? So as a result, CL tail is equal to AT, the lift curve slope, times alpha wing body minus IT, the pilot control, minus the downwash. Okay? Well, here's an interesting thing about the downwash. The downwash is not constant, you see. In fact, the more air you push down, the more downwash you will have, right? Isn't it? So when do you push down more air? How do you push down more air? Either you go faster or you have a bigger angle of attack. If the whole airplane has bigger angle of attack, you push down more air. So which ultimately results in having a bigger downwash over here. So the downwash itself is a function of the angle of attack as well. Okay, the downwash is not constant. So the downwash would look like this. So it would have a constant term plus del downwash del alpha wing body times alpha wing body, right? And this is the downwash when alpha is equal to alpha wing body, when alpha wing body is equal to 0, right? At alpha wing body equal to 0, that's this one here. All right. So then the lift from the horizontal tail will finally be AT times alpha wing body times 1 minus del eta del alpha minus IT minus theta 0. You see, you can complicate things really by adding more effects. By adding more effects to the whole thing. So ultimately now we have the tail now, okay? Add then the total lift will become CL is equal to CL wing body plus CL tail. So it will be CL equal to lift curve slope of wing body alpha wing body times 1 plus Yeah, I'm now putting this into the parenthesis now, this one, times AT tail A wing body times S 1 minus del lambda del alpha minus AT times surface of tail, surface of wing, or yeah, reference area, IT plus E0. Okay? So you might wonder where this is coming from, the ST divided by S, right? This is a surface area, the reference area of the tail, and this is a reference area of the wing. Okay? So where is it coming from? It is coming from the fact that CL, the lift curve slope here, the CL of the tail and the CL of the wing are not normalized with the same value, right? CL is normalized with the reference area of the wing, but CL of the tail is normalized with the reference area of the tail. You understand that? For example, I mean CL tail is lift of tail divided by 1 over 2 rho v squared times S. What S are we going to use for the tail? S of the tail, right? For the wing or the wing body, we are going to use the wing or the wing body, whatever that reference is. But if I take it in the same parenthesis here, in the CL alpha parenthesis, then I have to make that conversion here with the CL and CL alpha. Okay? So I can make it. I can take it into the same parenthesis as this one. So it is just in order to take this into the same parenthesis. Do you understand that? Okay? So now if you look at this, what you will see is lift curve slope of wing body constant. Okay? I'm going to put a blue check mark on the ones that are constant. This is constant. 1 is 1. Lift curve slope of tail, constant. Lift curve slope of wing body, constant. Area of tail, area of wing, constant. This one here, property of the aircraft, constant. Right? The slope. So this is basically a constant. So how about this one? AT, constant. Surfaces, constant. IT, pilot control. Okay, pilot control. IT is a pilot control. And this one here, it's a constant. So the only one that's not constant would be this one, but everything else is constant. Okay? For fixed pilot control, so if the pilot doesn't change the pilot anything, you could write for the whole airplane now, CL is equal to sum A alpha wing body plus times CL0. So you could call this part here CL0 and the rest here you could call the lift curve slope for the whole airplane. And then you get this one. And this is what we have seen all along. And this is for the whole airplane. Full aircraft. Including the tail, right? Including everything. And this is very consistent with airfoils and wings and everything. So you add the tail, everything to the airplane, and the airplane has still the same characteristic as an airfoil or a 2D wing. It still has this card. It's still a linear representation. This is still del CL del alpha. Okay? And this stall part, of course, I plotted, but this is really a line here. So what you're having here as an equation, you really have this, right? You have a line. And we know this doesn't go to infinity, and after a certain while you have this thing. What I'm trying to say is that the airplane still behaves like a wing or like a 2D airfoil. When I say 2D airfoil, I feel a little uneasy because 2D is this, and then when you take it to the side, it's nothing, right? So it doesn't really have lift. Let's say just an airfoil wing, a finite wing or something, right? It still looks like that. And that's, you know, this linearity that you see here between CL and alpha is why it is rather easy to fly airplanes, because you have this nice linearity. What if this curve was not linear, but it would look like that? It would be very easy to fly. Right? Not easy to fly, it would be very hard to fly. Right? You could do a similar analysis, and find relation for CM. And you would in fact find a very similar thing. You would find CM is equal to CM0 plus CM alpha times alpha. Okay? If you do a similar analysis like this, you would find this. And you can find this in books, you know, our reference books, the Bernard Atkins Atmospheric Flight Mechanics, the 72 edition, you will find how to obtain this formula as well. It's a very similar approach. And you will see at the end that you can actually plot this. And we know CM alpha does in fact look like this for the whole airplane. Straightforward? Good? Okay. So let's talk a little bit more about the control. The pilot control, longitudinal pilot control. It's the elevator. Okay, we touched it a little bit, but let's talk a little bit more about this. We call it the elevator. Now, let's say you have an airplane like that in hover, in forward flight. This is your CG, and this is your neutral point. You're flying very nicely in air, and you are in trimmed flight. Okay, so what can we do? This is my CM alpha graph, and this is my curve, and this is my alpha trim, and let's say I'm in trimmed flight and I'm flying forward. Now, the pilot wants to pitch up, put the nose up. How do you put up the nose? How can you put the nose up? What can you change in this picture? How about we change the CG? Can I change the CG of this airplane? If I change this location of the CG, will the airplane from this position go nose up or go nose down? Can I give it a moment? Will it go nose up or go nose down if I change the location of the CG? What do you think? Let's say this is an equilibrium. Okay, here's the weight. Here's the lift. Here's the drag. I don't know, I have a force here on the tail. I have an aerodynamic moment, Cm. What do you do? Let's say this is an equilibrium now. This picture is an equilibrium. If I change the location of the CG, will I have a change? Will I see a moment at the CG? Or will my nose go up or down? Let's put it that way. Yes or no? If I change the location of the CG, if all passengers run to the back and the CG moves here, will I have a nose up or a nose down? Of course, right? That's now easy. All passengers running to the back, nose up, right? Look at from this picture, CG is moving this way, so these guys will not have enough moment anymore. The moment arm will become smaller, and therefore not enough moment, and therefore nose up. Okay? Good. You'll get a nose up. So can I control the nose the nose up, nose down motion by changing the CG? Could I potentially do it? I mean, potentially. Put a weight, so I move the weight in the airplane. I could, right? I mean, I actually could. There would be a problem though. One problem would be you need to carry a lot of weight, and that would be not practical, right, for one thing. But there's one more thing. If you move the weight, you will also change the, what would you change? You would change the static margin. And because you change the static margin, you will suddenly start changing the slope of this curve, right? Which means the pilot will feel the airplane is suddenly behaving differently. I mean, at one point, if you had an alpha, the restoring moment was very strong, and in the second moment, the restoring moment was kind of slow, right? So it would change the way the airplane would feel in flight. So this is something we don't want. What we really prefer is to have this, alpha versus Cm. It would be great if this was a Cm alpha graph, and if I could just move this graph in a parallel fashion up and down. That would be really good. Because if I can do this, then the flight, since Cm alpha will still be a constant number, right? It is less than 0, but it is the same for all of them because the slope is the same. So it would be really nice so that the feel of the airplane would not change. Okay? The feel of the airplane, if you have a disturbance or how well it is flying, okay? It's called flying qualities or handling qualities. Let me write this down. Flying qualities and handling qualities. Okay? It tells us how good, how well does my aircraft fly. Okay? You can ask this the pilots. The pilot will have a number for it. It will say it flies good, it flies bad. And we call this flying qualities or handling qualities. How does the aircraft handle itself? Is it nice to fly, not so nice to fly? Okay? And in aerospace, we have certain scales that we can rate or classify airplanes. We say this is a handling quality level 1 airplane, which means it is a very nice airplane to fly. Level 1 is a very good airplane to fly. You might have other airplanes that are not so nice to fly. They are difficult to fly. We call them level 2. What does it mean it's difficult to fly? It means the stability characteristics are not nice. The input that you give, the airplane doesn't respond good enough. Maybe the tail is not big enough. Maybe the horizontal tail volume ratio was not good. So it's a level 2 aircraft. And an airplane that is really bad to fly, we call it level 3. Okay? So we are rating airplanes one after another. So if you're first designing an airplane, someone will tell you often a requirement. It will say, build me an airplane that is at least level 2. Or, I mean, nowadays it's always like, build me an airplane that is level 1. I don't want a level 2, not a level 3. So how do we decide on these level 1, 2, 3s? Well, we call it, there is a scale, okay, and it's a Cooper-Harper rating. Harper rating scale. This is an A. Cooper-Harper rating scale. This is badly written. Harper. Okay? So it's a scale that's basically a questionnaire. You can go on the internet and type in Cooper-Harper. You will see the scale. It's not very complicated. And it goes from, it has level 1, 2, 3. And each of them has an additional subcomponent, 1, 2, 3. So it has questions to the pilot. It says, how did the airplane handle itself? You know, what did it do when you were doing a turn? What did it do when you were going down, up? And all these questions. And the pilot is filling it out. After he or she fills it out, you will get a scaling from that. Okay? And you do this not with one pilot, of course, because it's a subjective information. You do it with 3, 4, 5, 6 more pilots, right? And then after that, you add up the questionnaires, the answers, and you can classify your airplane how well it will fly. Now, for you engineers, it shouldn't be a surprise when you do everything right about your airplane design. If you move the CG to the back and the pilot says, oh, I can't fly this airplane anymore, don't be surprised, right? You put the CG to the wrong location. Also the slope, I mean the slope is, if the slope is too much, it's not good. If it's too little, it's not good either, okay? So for this, there are specifications. Of course, there are books, there are specification books that tell you what would classify as a level D. What should you do to your airplane so that it is a level D airplane, all right? One of the things is that, for example, if you would change the CG location and you keep changing this, the pilot will feel at one point a very stable airplane, and on another instant in flight it will feel an airplane that's not so stable, right? It would have a slow restoring moment. But if you do this, it would be very nice because at all times it would feel the same restoring moment, right? If you could do this. Of course, the alpha trim would change with it as well, but that's another issue that we need to look at. But at least the handling qualities or the flying qualities will sort of be still the same. Okay? So that's kind of important. Now, how can we achieve this? The elevator at the back is exactly doing this. Okay? That's why the elevator is such a great device, because it is actually moving the CM alpha curve parallelly up and down. Okay? So let's see how that works, how this is actually achieving this. Okay? This is what's important. But because I know if I move the CG, I will get an extra moment, nose up and down, but it will cause this, which will not help me with handling qualities, plus it will be kind of not easy to move the CG of an airplane anyway. Okay? So, okay. First of all, if this is my horizontal tail, right? This part here. Oh, let me plot it again. I didn't like that plot too much. Let me do it this way. this. And you might want to move it down like that. Okay? And this is the horizontal tail again. And this move, I called it IT in the other one because it was a pilot control. Let's be more specific. This is del E, and this is a positive direction del E, and we call this the elevator control. Okay? So if this moves downwards, basically creating more lift upwards, we call it a positive elevator input. Okay? So if the pilot gives a positive elevator input, will I have a nose down or a nose up? Nose? Down, of course, right? Because you put it down, more lift, you will have a nose down. Okay, for a positive elevator input. So this is the sign convention. If it goes the opposite way, right? If you would move it like that, this would be a negative one. That's a positive. All right? Good so far? Okay. So if I do that, the additional lift that I will create with a positive del E will look like this. Right? This is the change of lift because of del E. Okay? Is this number a positive number or a negative number? Del CL, del E. Partial derivative, change of elevator inputs. What will happen to lift? The change in lift because of elevator input. Is it positive or negative? It's positive, right? For the positive elevator input, more lift, and therefore the lift will be positive. Right? Obvious. Okay. And we just answered the question. Del CM del E times del E. This is the change of lift because of del E. Is this number positive or negative? The partial derivative, this one, must be negative or positive? Negative, of course, because if you have positive like this, you get more lift on this direction, and because you get more lift in this direction, you will have a nose down, so it will be a negative moment, isn't it? So that should be negative here. So del CM del E, it's a partial derivative, okay? It's typically negative. Okay, it's typically negative. Okay, so CM new will be CM that we already had in trim, right? Or we had a certain CM, which is alpha of the airplane, plus some delta CM. This is because of pilot input, del E, elevator, and this is what we had before, was there before. Or I would rather say the moment because of aircraft only, no input. Okay, this is with input. This is now with input, with the pilot input. Of course, this is a function of alpha. We know CM is a function of alpha, so it is equal to CM alpha plus CM del E times del E. So if you plot this, it will look like this. Cm versus alpha. And let's say this was your original graph. And note that this is not a function of alpha anymore. This is just a function of del E. Okay? So here's my question. Which way will this plot move if I give a positive del E? Will it go up or will it go upways, up or down? Up or down? Down, right? Because it will give you a nose down moment, the pitching moment will reduce, so it will be going down here. And it will be equivalent at all points because this is not a function of alpha, it is just a function of del E. So this is for a positive delta E. If you would give a negative delta E, this would be moving upwards. It would be moving this way, and this would be for a negative del E. Okay, we are almost done with this. Any questions here? You understand why we are using this instead of doing this? We really like to do that. Here's a good question to ask. What is del E in trim? Right? Because in trim, the moment must be equal to 0, so Cm must be equal to 0. There are two conditions for this. I mean, for the numbers that we looked at, there are two things. First of all, Cl must be equal to Cl trim. Right? Because you still need the lift to fly. Secondly, we need Cm is equal to 0 in moment. The moment must be equal to 0 in the longitudinal direction. So you could really say this, Cm is equal to 0, and that's equal to Cm0 plus Cm alpha times alpha trim plus Cm del E times del E. You see, when you are in trim, Cm is equal to 0, but that corresponds to alpha trim, right? I mean, we always keep plotting this. Let's see, Cm is this and alpha is this, right? And I keep doing this. This is alpha trim. And I told you this alpha trim must do two things. First of all, it must generate Cm equals 0, but it should also be enough to fly. Because alpha trim is also this, right? Cl alpha. And let's say this is alpha trim, and this is the Cl that you need to fly. Right? You need Cl alpha trim to fly, and alpha trim is... So these two alphas must be the same. It should give you enough lift to fly. It should also put your moments equal to 0. So you need to solve this together in order to find that position. Fortunately, what we do is the following. Look up here. We first find this alpha trim that will generate enough lift, because lift, let's say, must be equal to weight, approximately. It's not always the same, but you know, you find your lift. And then you find your alpha trim. Let's say your alpha trim is not here, but it is here. What do? Now you can use your elevator to move this line here. You see? And that's why this elevator is so useful now. Because if your alpha trim is not here, you find your alpha trim that is required to carry your lift and carry your weight. Okay? And the same alpha trim you need to find over here. Let's say this alpha is not enough. So what do? It's here. Okay, good. So I move this curve by using my elevator control. That's why the elevator control is so important to trim the airplane. You see? All right, so this is the first one. And del E is over here. This is the moment equation. And we can also write the lift equation. CL trim, like over here, is equal to CL alpha times alpha trim plus CL del E times del E trim. Well, let's just call it trim. Okay, del E. Because the del E will also create some additional lift. I mean, the tail, lift due to tail. Okay. Now you have two equations, and you can hopefully find the trim from this. CMN CL trim. So you write these two equations in matrix form. Okay, so I just wrote these two equations in matrix form, and these are the unknowns. So solve for alpha trim and del E trim. Okay. All you need to know now are these aerodynamic derivatives: CL alpha, CL del E, CM alpha, CM del E. And this is the trim lift that you need, and this is the CM0 of your airplane. And you have two equations, two unknowns. You can actually solve for alpha trim and del E trim. So then you know at what alpha your airplane must be and how much pilot control you need at the elevator in order to fly in trim. The pilot does it naturally, right? If the airplane is falling down, pulls the nose up, but it doesn't pull it too much up, because then you will do this, or too much down, you will do this. So the pilot kind of does it naturally, okay? Pull the nose up, because then you will have drag, you will slow down, so it will increase the thrust, and you will be leveling out. And the pilot will automatically put the airplane, or naturally put the airplane, into an alpha and into an elevator position, so that the airplane can fly forward in a constant trim velocity and constant trim altitude flight condition. Okay. So this is how you establish a trimmed flight condition in a longitudinal direction. We haven't looked at lateral yet. Okay, this is only longitudinal direction. So any questions? Okay, so let's stop here. And if you want to read more about this, listen, just give me 1 more minute. if you want to learn more about this, I mean, you know, 3 hours is not enough to go very deep into these things. You might learn a lot more, there's a lot more information about this in literature. And the two references that I gave you, the two books by Bernard Etkin, the 1972 edition and the 1996 edition, they give you a lot of information to read, okay? But these are the fundamentals. I'm trying to cover the fundamentals in this class so that when you go back and read something, you know where to start and what is what, okay? So if you have time, please go back and read those books. So about next week, I will let you know about our class, when it might be, if it's going to be, or maybe not. I will let you know. Look at your emails. And on the 16th, we have our midterm number 2. And please submit your homeworks. When are they due? When are the homeworks due? What? 12th of May. That is next week. Please, if I'm not here, submit it to the assistant, Hazal Altu. You know her room? Okay. Please submit it to the assistant. If I'm not here. If I'm here, bring it to the class. Okay? All right.